Hello, everybody, and welcome back to Build Stuff Live and Online 2020, streaming to you live from all over the world to all over the world through the magic of the internet. Now, our next speaker, our final speaker for day 2 of Build Stuff, is a professor of computer science at the University of California, Los Angeles, UCLA. Research interests are compilers, embedded systems, programming language, information security, software engineering, recipient of the ACM SIGPlan Distinguished Service Award in 2012, currently the chair of ACM SIGPlan, I believe, and on the editorial board of the Information of Computation, and he's joining us live to talk about quantum computing and the quantum internet. Please give a big warm Build Stuff welcome to Jens Palsberg.
Oh, hi, everybody. So quantum computers are here, and they're getting better at a double exponential rate. And now researchers are building the quantum internet that will enable quantum computers to work together and work together with unprecedented security. And quantum computers promise to break security, to simulate chemistry fast enough to discover new drugs, and to beat classical computers at the optimization problems that industry solves every day. And so what I want to do today is to take a look at how far are we with this and how does it work. And my goal really is to persuade you that quantum computing and the quantum internet are developing fast, really fast, and you should think about joining the movement. And so So I'm going to go over 3 points to support this. I will give the review of quantum computing, and then I will talk about how quantum teleportation is essential for the quantum internet. And then my big illustration is going to be quantum chess. That's what I'm going to use to illustrate the concepts. And so what is quantum anyway? And I just sort of, before we get too far into this, I just want to show you a qubit. This is a qubit. It's a vector of 2 elements, and alpha and beta are both complex numbers. And the situation today is that the largest quantum computer we have is at Google. It has 72 qubits. Other companies like IBM have quantum computers that have many qubits, above 50, and the number of qubits is growing all the time. And the magic is that if we have a quantum computer that has 72 qubits, we are computing with 2 to the 72 complex numbers. And so this exponential is the key to the power of quantum computing. And so 1 qubit, 2 complex numbers, and then every time you add a qubit, we double. And so it means that if one day, which may arrive in just a couple of years, according to studies from the National Academy of Science in the United States, maybe we will have 300 qubits. And so 300 qubits would mean we are computing with 2 to the 300 complex numbers, which is more atoms than in the known universe. And so it's just a humongous amount of computing power. And that computing power is really what we want to harness in quantum computing. And so let me just take a moment to talk about why are all these numbers complex. And so now we are going to the heart of quantum mechanics. And Feynman said that the essence of quantum mechanics is the double slit experiment. So a little physics experiment that goes all the way back to Thomas Young in 1801. And it happens to be an experiment that many of the high schoolers in California, where I live, do as part of their high school experience. And I just want to illustrate that experiment a little bit. So here is... over to the left, we have some light, and we are shining light towards the right. And over all the way to the right, we have a wall, and the wall is marked with a little area P, where we are sort of taking up an interest in whether any of all those photons that are coming with the light are hitting P. And so really, we want to know we want to think about the probability that a photon hits P. And so then to make the experiment interesting, we're going to have a wall in front of the wall. So that's the thing in the middle of the screen, where we make 2 openings, or as the people like to say in the experiment, 2 slits. And so it means that a photon it sort of can go through one or the other. That's sort of how we could think about it. And so it means that now we can start to say, okay, we have the total the sort of, for all the photons coming through, we can talk about the probability that they will hit P. And then we can talk about, suppose we close up one slit, how many photons do we then get hitting P? Or if we cover up the other slit, how many photons will then hit? And then we should think that the sum of those two would be equal to the total. But that's not true. And that's the essence of the double slit experiment. If we think of probabilities in the usual way, where probability is a number between 0 and 1, a real number between 0 and 1, and you try to add up the probabilities of the first slit and the second slit and hope you get the total, it's not going to work. And what they found out in quantum mechanics is that if you instead start to think about probabilities as complex numbers, then it works. And you actually get that you can sum up, and everything is totally right. And so, so it means that step one in quantum mechanics, and therefore in quantum computing, is to change from thinking about real numbers in computing to think about complex numbers. And so this is where the famous slogan of quantum computing comes from. God plays dice, but they are not normal dice. And so when we go all the way down to the basic qubit of two complex numbers, these are the complex numbers that we are looking at. They are the complex numbers that come from this kind of thing, and they are all over in quantum mechanics. And so this means, does that mean we have to know quantum mechanics to learn quantum computing? And fortunately, the answer is no. I can say for myself that I don't really know a whole lot of quantum mechanics, but I am learning quantum computing as fast as I can, and I don't need to know quantum mechanics. So I'm sort of living proof that this works. And so let's just look a little bit at what the situation is. So we compare with classical computing as a normal computer as a device for doing Boolean algebra really fast. And we know we can do Turing-complete computation. A quantum computer is then a device for doing linear algebra really fast. And the sort of the subtitle here is that, by the way, linear algebra is not Turing-complete. It's linear algebra of a restricted form, where we can only do certain things. But if we can do them, we can do them very, very fast, and we can scale them way up. And so that way, this picture is already suggesting quantum computing's place, which is as a, let's call it as a device, a subroutine, an accelerator for classical computing. Once we have quantum computers, the classical computers will still be leading the computation. And then the quantum computer will do what it's good at, and it'll be there for doing certain things very fast. The classical computer will still be doing the main stuff. And so in a way, this is what the whole field of quantum algorithms is about, is to find out how much can we put over there in the second column of quantum computing so that we can get it done fast. Underneath the hardware in classical computing, well, we know it's semiconductors using classical mechanics. And in contrast, quantum computing is based on quantum mechanics. And for example, the quantum computers that are built by IBM and Google, and another one is Rigetti, and nowadays there's also one coming online from Intel. They are all built on superconductors, and so a very different technology. And nowadays there are many more examples of hardware technologies for quantum computers, and they all have the same idea. They wanted to get us to a qubit and then be able to build up qubits that give us this exponential effect. And so what do we do when we have a classical computer use a quantum computer as a sort of as a subroutine or as a helper? And so we get a picture like this. So the classical computer starts with some bits, and then we will load up those bits as qubits in an initial state on the quantum computer. Then we can do quantum computation. We still end with some more qubits, and then there's a step called measurement that then gives us back bits. And as it happens, if you, for example, run on Google's quantum computer working with 72 qubits and you measure, you get back 72 bits, which is maybe sort of a little bit disappointing, because having 72 qubits, having 2 to the 72 complex numbers, and then all you get out of that is 72 bits, looks a little meager, but that's exactly what's going on. The reason why we can do this picture without knowing quantum mechanics is that there's this interface between the software and the hardware level that is guided by 4 axioms, 4 rules, 4 postulates that sort of keeps quantum mechanics at an arm's length. And so those postulates say the following. The first postulate says that the state is a vector of complex numbers. We talked about that. The computation, which is the middle part of this picture, is to take steps, and each step is to apply a matrix. So that's really all quantum computing does. It applies a matrix. So it's really true that quantum computing is like applied linear algebra. And the third thing is that when we measure, when we reach to the final state, we can do this measurement, and we can get this partial information of mapping a lot of complex numbers to some bits, to not very many bits, it seems. And so it means that quantum computing is really about applying vectors, applying matrices to vectors of complex numbers. And so this turns out to be plenty for what we want to do. So we know that quantum computers, once they get large enough, can factor integers using Shor's algorithm, which comes with the promise of breaking some of cryptography. Another application people are excited about is simulating quantum chemistry for the purpose of discovering new drugs in particular. And that was actually the original motivation when particularly Feynman popularized the idea of quantum computing, was to do simulation of quantum chemistry. And then there's the whole idea of solving NP-complete problems, which of which, for example, NP-complete optimization problems is a big category. And it turns out that quantum computers are wonderful for finding approximate solutions to NP-complete problems very fast. And so those are some of the promises. So in quantum computing, there are 2 words that sort of distinguish quantum computing from classical computing, and I want to talk about them a little bit now, and then I want to go back and illustrate them using quantum chess later. So first, there's the concept of superposition, and so superposition means that when we're doing this computation in the middle of this picture here, we are really computing with a linear combination of basis vectors. And so that's really when I'm saying that the state of a quantum computer is a vector of complex numbers. Of course, we can think of that vector as a linear combination of basis vectors. And so that's the quantum computing people like to call that superposition. And so let's just get that on board. And of course, the constants in the linear combination happen to then be those complex numbers that we get from quantum mechanics. Second word in quantum computing is entanglement. And what entanglement means is that you have 2 qubits, and then you measure at the end, here the third step of this picture. And what you get, you always get the same bits for those 2 qubits. And let's just look at what this means in terms of notation that the quantum computing people like to use. So here is a state of a quantum computer with 2 entangled qubits. And so I've written it up in 2 different ways. On the left is the way the quantum computing people like to write it. It's called Dirac Notation, after Professor Dirac. And what it says is that if you look between these funny brackets there, which are normally called kets, we have 0, 0. And so what this is saying is that one possibility, so to speak, is that the 2 qubits are 0 and 0. And then plus 1, 1, that means another possibility is that they are 1 and 1. And so those are actually two basis vectors. And you can see that more clearly if you go over to the right, where the 0, 0 is the one that leads to the 1 up on top of the vector, and the 1, 1 is what leads to the 1 at the bottom of the vector. And then there's a rule, which is that all vectors in quantum computing, let's say the state of the quantum computer, always has to be a unit vector. And to make that happen, we multiply the whole thing by 1 divided by square root of 2. And let me just say, that's like the most famous number, most used number in quantum computing, 1 divided by square root of 2. If I had $1 for every time I read 1 divided by square root of 2, I would be a rich man today. So let's take a look at how does a quantum computer create an entangled state. And so you can imagine we're starting with something simple, then we are going to create the state. And if we measure this state, we are going to get either 0, 0, or we're going to get 1, 1. And as it happens, if one reads the math correctly, you're going to get either one with probability 1/2. So that's how the math works out. So it's entangled, and so we will get the same 2 bits when we measure, but we don't know what we're going to get. We're going to get them with probability 1/2 and 1/2. So I'm going to create this state now with a little program. And so here's my program. So we're going to load up some bits. And so I'm going to load up so that qubit 0 is represented by this ket 0, which is really a basis vector. Actually, just the basis vector 1, 0. And qubit 1 is, with typos and all, it's supposed to be a 1 over there. So ket 1. And that's actually the basis vector 0, 1. Now we are going to do some quantum computing here. So we're going to apply 2 matrices. And for the time being, I'm simply going to say we have 2 matrices that are, I'm sorry, the second qubit 1 is going to be in state 0. It's not going to be in state 1, as I said. It's going to be in state 0, as the picture is correctly saying. Both qubits are going to be 0. So now we have 2 matrices, and we're going to do a multiplication of 2 matrices in order. First, there's this H matrix, and then there's this C0 matrix. And so the deal is that the H matrix is a 2x2 matrix, and it operates on 1 qubit. So we are applying a 2x2 matrix to a 2-dimensional vector, and of course we get a 2-dimensional vector out. Then the C0 gate is so people like to call them gates in quantum computing to make them feel more like the gates of classical computing, but they are matrices all the same. And so this second part of the picture here is illustrating the C0 gate operating on both qubits, and it is so C0 is a 4x4 matrix, so it can operate on 2 qubits. And as I've said, when you have 2 qubits, you have a vector of size 2 to the 2, which is 4. So it all makes sense. These 2 matrices, they look like this. So the H matrix is also called the Hadamard matrix, named after Professor Hadamard. And then the C0 matrix, it looks like this. And so they are what they are. And as it happens, if you work out the math, you will end up in this entangled state, as we talked about it before. And that is good, because entanglement is essential for a lot of what we want to do in quantum computing. And in particular, we like to connect quantum computers. And so that brings me to talk about the quantum internet. And so I live in the United States, so let me talk about some of the efforts in the United States. This year, the White House called for development of the quantum internet, and now there are multiple centers in the United States alone, and most likely other places in the world, that work on the quantum internet. There's a $51 million NSF Engineering Research Center led by Saikat Guha at University of Arizona. They're working on the quantum internet. Another one is a $25 million NSF Quantum Leap Challenge Institute led by Brian DeMarco at University of Illinois. And they are connecting quantum computers. And so this brings up this question of how will the quantum internet work? And very soon you will see that this picture in front of you is part of the secret to how it's going to work. And there's a big challenge that we have to overcome before even getting out of the gate with the quantum internet. And that is that in quantum computing, there's a fundamental theorem called the no cloning theorem that says that we cannot clone an unknown qubit. So if you have an unknown qubit and you want to make a copy of it, like we do in classical computing all the time, we have an unknown word in memory and we want to make a copy. You cannot do that in quantum computing. You simply can't. It's going all the way to the heart of quantum mechanics, why this is impossible. So this means if you're going to build an internet, the first problem you want to solve is to build a quantum repeater that can allow you to help propagate a message over long distances. And if the repeater is set up to work so that it takes in a packet, an unknown packet, and all you want is to forward it. So you are copying from the inbound to the outbound. Quantum computing says you can't do that. That violates the no cloning property. So how are we going to make progress on that? That is the question. And the answer lies very much in this picture here, which is that we can do entanglement. And the way the quantum people use that to get going is quantum teleportation. And so there's it's like a two-stepper. First, you go from the idea that we can create an entangled state, like I showed, and then you use that to build quantum teleportation, and then you're ready to build a quantum repeater. And so what I will do is that I will talk about how quantum teleportation works. And I am going to imagine that Alice has a qubit. This is her qubit. So it's this is how the general qubit looks like, written in Dirac notation. Alpha and beta are complex numbers, like always. And Alice wants to tell Bob this qubit. And so she's so of course she cannot make a copy of the qubit and send it to Bob, really. So what she will do is instead she will send classical bits to Bob and enable Bob to recreate this qubit. That is what quantum teleportation is. And to get going on this, we're going to need the state from before, this thing. And so what I will do is that I will say, Alice and Bob will share this entangled 2 qubits. So we know we can create them. And let's just for a moment imagine that Alice and Bob can share them. And so Alice has her qubit over here, and then they share these 2 qubits. So this means that when it comes down to it, Alice has the stuff in the red box. And so I'm going to go light on the notation, but this is all notation from quantum computing. But what it boils down to is that really Alice has 2 qubits, and then the third qubit is Bob's qubit. And what Alice will do is that she will execute this little quantum circuit here. They like to call them circuits. So again, you see CNOT, you see Hadamard. So she's using them again, a little bit different way. So she will apply those to her 2 qubits, and then she will send, and then she will measure. And so we know that when you have 2 qubits and you measure, you get 2 bits. And then she will send those 2 bits, classical bits. She will send them over the regular network to Bob. And then Bob will receive them. And now let's see what Bob can do. So we know that, we just keep in your mind that Alice has this thing with alpha and beta, and we want Bob to have that. And the question is, how is that going to work? So I'm going to take just a minute to show you how math works in quantum computing, just a little bit. So here's just 1 page of calculation, where the idea is just to show you roughly how this kind of thing goes. And so we start up in the left corner with these 3 qubits. So we know how they're shared, who has what. And once we start calculating, then we can sort of expand this out. So we have this kind of thing here. Now Alice applies her stuff, her 2 operations there. And at that point, the state of all the 3 qubits is this thing in the middle. So some computation happened. And at that point, oh, so this was after the. So I sort of short-circuited myself. This is after Alice is going to apply C0 first, and then she's going to apply H second. So this is the middle state here is actually the middle. That's the state we get after she applied the first operation. Then she's going to apply H to her first qubit. So actually this one over here, and at that point we can do some more calculation, and we end up with the bottom line down here. And so I have factored out things very nicely because I want to make a point. So this thing down here, you see the plus, plus, plus. What this is saying is, again, that we have a linear combination of stuff, and Alice's 2 qubits are always the first two. So you can see that she either has 0, 0, or 0, 1, or 1, 0, or 1, 1. That's what you get when she measures, because if she measures 0, 0, she will get the bits 0, 0. If she measures 0, 1, she will get the bits 0, 1. The third qubit is in whatever state it's in. You can see it's a little bit different every time. But Alice can now measure, and as it happens with probability a quarter, she will get one of these 4-bit patterns. And so what she does is that she measures her qubits, gets one of those 4, sends those 2 bits to Bob. And there's Bob. And Bob is, of course, sitting and looking at his qubit. And because of the entanglement, his qubit is now in one of these 4 states. He doesn't know which one, of course. He cannot inspect his qubit, but it's in one of those 4 states. And what Bob will now do is that he will do a little bit more computation. So here's like the overall picture of quantum teleportation. Alice starts with this qubit. She does a little bit of work. She measures, and then she sends her 2 bits that came out of the measurement to Bob. Bob will do a little bit more computation, which is there's also something called X and Z in quantum computing. So Bob does something like this, whatever it is. And so these are other matrices, and ends up with magically Alice's qubit. And so how does that work? So it turns out that if we look at it, these operations with X and Z that Bob is doing, what he's doing is that he's looking at his qubit, which is always the one in the blue box. And depending on circumstance, what these X and Z are doing is that either they swap the 0 and the 1. So you can see if we swap the 0 and the 1 here, we get everything ordered alpha 0 and beta 1. Or it will flip the sign of beta, which will get this minus flipped to a plus in the right places. And sometimes we do both. And in all cases, it works out, and Bob ends up with Alice's qubit. So now you should ask yourself the question, if we cannot copy a qubit in quantum computing, how did we manage to get this qubit over to Bob after all? And the answer is, we destroyed Alice's qubit. And so that's the only way this can work. You can move this qubit around by quantum teleportation, but you cannot copy it. And so that's the thing here, is that the qubit moves, but it doesn't really get copied. Copied would violate everything, but moving around is okay. And quantum teleportation is what makes it work. And this has been demonstrated. 2016, researchers from Calgary in Canada used the fiber cable network in Calgary City to teleport qubits over a distance of about 6 kilometers, which is what we would call about 3 miles over here. And then in 2017 was the famous experiment where researchers in China teleported a qubit from a satellite in orbit and down to Earth. And so that's a teleportation going on over 1,400 kilometers. That's up around 900 miles. Those experiments were like a single step. They were not using repeaters. They were doing a single step of teleportation. And so this brings up the question of, can we actually then use teleportation to build a repeater? And this year, 2020, it's an exciting year. Lukin, in his lab at Harvard, Lukin and his students and postdocs demonstrated how to build a repeater on quantum teleportation. And so that is sort of very recent news. It started working just months ago. And so it means that we have really set up for this picture at the top, where we have on the quantum internet a sender and a receiver, and each step is teleporting a qubit. The sender will teleport to a repeater, the repeater will maybe teleport to another repeater, and then that repeater will teleport to the receiver. And so the deal is, we know that the qubit only is there in like one place at a time, but we can communicate it. And with the repeaters, we will be able to communicate this over long distances. The challenge, of course, is that we need to be able to share these entangled states that I showed, but people are getting better and better at that. And so once that happens on the grand scale, we will have the quantum internet for real. And I want to say one more thing, which is what's illustrated that by this picture that you can find on Wikipedia, which is that we want to do more than teleport a qubit. We want to be able to entangle a qubit on my quantum computer with a qubit on your quantum computer. And so to do that, we need to do more than share a single qubit. Now, what this teleportation stuff that's hang on. We need to do more than share an entangled pair of qubits. We need to share a pair of entangled qubits between each of the steps in the chain. And if we can do that, then we will be able to entangle qubits on two different, maybe physically very distant quantum computers. And that's when the quantum internet becomes really powerful, because now we can start to think about using all the quantum computers together to do a single big computation. Okay, so those are the concepts of the quantum internet, and so now I've talked a lot about quantum computing, of superposition and entanglement, and how we can use it. And I just want to give an illustration in a different way. That's more pictures and less math. And that is quantum chess. I have Steam on this laptop I'm using to show you all this, because I log into Steam to play quantum chess. And this is a screenshot from quantum chess that I took the other day. And so I want to give a sense of how Chris Cantwell at USC, which is University of Southern California, very close to where I am here, used the concept of quantum computing to build a quantum game. And I can then use that to very easily illustrate the concepts of superposition and entanglement. And so chess, of course, classical game, many people know about it. It is as classical as it comes in many different ways. And really what we want to do is to build this layer of quantumness on top of it. And so what you see in the picture here is that we have white has a king and a pawn and a knight, and up here black has a king and a pawn. And so it all looks very classical at the moment, and it is sort of a classical state. Of course, in quantum chess, a state can be entirely classical. The board can be in a classical state. But now let's start to think about what happens if we move into quantum states. And so in quantum chess, the way Chris defined it is that you can certainly do a classical move if you want to, but you can also do a quantum move. And the way a quantum move works is that you move, in this case, for example, I could think of moving the knight 2 steps. And so, for example, I could move the first step the knight would move. The first move would be up here to e5. And then after that, I do a second one right away to c6. And however, I will only do that with probability a half. So 50% chance it stays put, and 50% chance that it does 2 moves over to c6. And so this means that if we make this happen, we will now get the following quantum state, which we can think of as a linear combination of 2 possibilities, or as the quantum people would say, a superposition of 2 boards, really. Half of the time the knight is on f3, half of the time the knight is on C6. So that's superposition. Okay, so now it's black. And so now black, of course, could think about moving this pawn 2 steps forward from C7 to C5. And that kind of depends on whether the knight is in the way. And so it means that this very classical looking move of the pawn moving 2 steps forward now kind of depends on the knight. And so it means that doing that move entangles the pawn and the black pawn and the white knight. And so we get ourselves into a situation like this. So I just moved what I had on the right. I moved over to the left. And then what I'm showing here is that the pawn will move forward 2 steps with probability a half, which is the case where the knight stayed at f3, and in the case where the knight actually moved. So now you can see we have actually entangled the knight and the pawn. So even though it looks like the knight is here and there half of the time, the pawn is here or there half the time, they are actually entangled. We are really only looking at 2 possible boards, not 4. So that's what entanglement means in a way, that it could look like we have 4 possible boards, but we really only have 2. So now it's white. And so what is white going to do? So white could think about moving a pawn 1 step forward. So this definitely also is depending on whether the knight is in the way. And so of course, maybe the knight moved to c6, the black pawn stayed put, and then the white pawn is free to move 1 forward. So if we do that, let me again move the right picture over to the left and then move the pawn. Hey, so the pawn moved 1 forward because the knight had gone and the black pawn stayed where it was. And so you can see what happens here is really a measurement. We find out exactly where everything is, so we are back to a classical board like before. So that's one possibility. The other possibility is that the white pawn couldn't move because the white knight was still there. If the white knight was still there, the black pawn moved. And so now again, the measurement revealed that we got the other one. So this is exactly like if you're back to this entangled pair of qubits from before. 0, 0 is like the pawn moved and the other stuff happened, the knight moved and so on. And 1, 1 corresponds to this picture here, where the pawn has to stay where it is because the knight stayed where it is and the black pawn moved. And so that's quantum chess. So that's what people are playing with. And you can imagine we can entangle more and more pieces and pawns as we play, and the whole thing can get very complicated. And you can go to YouTube and find videos of people playing quantum chess and having fun with this. And lots of stuff can happen. One of the things about quantum chess that one has to be aware of is that quantum computing in general is always reversible. So in quantum computing, all the matrices that we use are reversible, are invertible matrices. So it means we can always go back. We can always just apply the inverse matrix and we go back to where we were. And so one can wonder, how does that work in chess, where we can take somebody's piece and the piece gets moved over to the wooden box to the side and is out of the game? We model the box too. So it means that at any given time, the state of the chess game is both the pieces you can see and also the pieces that have been moved over to the side. So they're not on the board anymore. And so, of course, in that sense, we can in principle always move the pieces back to the board. That's not what we do in chess, but to make sort of a reversible chess game, one could do that. And so that's actually how quantum chess models the chessboard. And then there's a last thing for those of you who want to go out and take your favorite game and make it into a quantum game. There's one rule that Chris put on top of all this other stuff, which is only 1 piece per square. It's a rule that we are very used to in chess. There can only be 1 piece per square, but now that pieces can start to be here and there with probability something less than 1, does that mean that we could have the same, that we could have multiple pieces on the same square, maybe with some low probability each one. And in quantum chess, as you will find it on Steam, the answer is no. One piece per square, even if that piece is only there with probability, say, a half. Okay, I want to say one thing at the end. I want to say one thing at the end. What about team play? So I want to point you to something else you can find on the internet, which is called the Magic Square game. And what the Magic Square game does is that it sets up two players who are playing together on the same team, and they're trying to win. And the game has to do with, it's actually a famous game. The game has to do with that there's a referee that says to Alice, I give you a row and you fill in bits that sum up to an odd number. And then completely independently says to Bob, I'm going to give you a column and you fill in bits that sum up to an even number. And the objective of Alice and Bob is to, in whatever one square that intersects between Alice's row and Bob's column, they want to get the same bit. If they get the same bit there, they win, and if they don't, they lose. And it turns out, of course, if they cannot coordinate at all, if this is completely independent, it's totally random what's going to happen, and we can work out the win probability and the lose probability. And it just happens that if Alice and Bob do what they do at random, they will win as a team 89% of the time. And then let's think about making this quantum in the following way. They can share these entangled pairs of qubits, like we've seen before for quantum teleportation. Now they can share something, and they can do something with these shared entangled qubits. Does that help? And the answer is yes. So the mathematicians have worked out that if they can share free entangled qubits, so 1, 2, 3, they have enough that they can coordinate and win this game 100% of the time. And so that's, again, a sign of that once we go quantum, we can do more than we can do classically. Okay, so I'm going to stop my review here. So I just want to say quantum computing is developing very fast. The quantum internet is developing very fast. It's an exciting field, and these people need software. They need software of all kinds. Of course, they also need quantum algorithms. And so for all you people out there who know how to build stuff, the quantum field needs you. And I think I've made the point why I jumped into quantum computing some years ago. I'm a software person by heart, and I could see that this is a field with so much excitement, and this field needs software. And I encourage you to think about whether this is something you could be working on. Thank you.
Thank you very much, Jens. That was mind-blowing. That was definitely one of the most information-dense talks that I've seen in a while, but really... No, that was great and really, really interesting. Quantum computing is one of those fields that, I've never worked in directly, but it comes up once in a while. It's one of those things I think all of us in the industry need to be aware of what it potentially could mean and the potential. And, also it's one of those things that makes the mainstream press, and they're like, oh, there's this new quantum computer that means that everyone can get your credit card number. And, we're not at that stage. But one day we might be, and it's we're the kind of people who the world is going to ask us, like, are they right? Is this really a thing yet? So we got a lot of comments in the talk. Great talk, feedback, great talk, mind blown. Somebody says that their brain's qubits are now entangled, which I guess would that make you telepathic if you could entangle brain qubits with somebody else?
Man, that's where we're going.